Today we will look at probability. Probability is a matter of proportion. How many items are of interest to us out of some total number of items? For example, suppose we had 2 red balls in a bag and we had 4 blue balls in the bag. And we stick our hand in the bag and pick out a ball without looking. So we're asking the probability of getting a red ball. Well, since there are the total number of balls in the bag is 6, so we're going to be looking at the proportion out of 6. The proportion out of 6 is 2. 2 red balls out of 6. So the probability of getting a red ball is 2 out of 6. How about combining? Suppose we want to look at the probability of getting a red ball. We do not replace it, and we look at the probability then of getting a blue ball. So we would look at this as being the probability of a red ball multiplied by the probability of getting a blue ball just after it. So the probability of a red ball followed in by the probability of a blue ball. And of course, that is going to be the probability of getting a red ball, as we've already seen, is 2 out of 6. And that will be multiplied by the probability now of getting a blue ball. At this stage, 1 ball is gone. It is not replaced, so there is only 5 balls. And 4 of the 5 balls are blue. So it is 4 out of 5 is the chance of getting that. And when we combine those together, 2 4s, 8. It's 8 out of 30. Another way I suppose of looking at this is that there are 30 possible ways of drawing out these 2 balls together, because there's 6 balls to begin with, and then there's 5 balls. And so there's 30 ways of getting them. But we're in particular only interested in getting a red ball first, which is 2 ways, and 4 ways of getting the blue ball. So there's 8 ways of getting what we want out of the total of the 30 ways. Another way of looking at this could be in terms of what's called conditional probability. In other words, that second probability depended on what happened the first time. Because so really, that's the probability of getting B. So in a way, that's the probability of getting a blue ball, given that you'd already gotten a red ball. So that's what that second one is the probability of getting a blue ball, given that you have already gotten a red ball. The probability of getting that red ball doesn't matter for this part. This is looking at the probability of getting the blue ball, given that you already had gotten the red ball. So if you had already gotten the red ball, you're down to 5. And so you have 4 blue balls out of 5. So this bar here means given that. And this idea of conditional probability is quite important in things like tests for diseases. That's why it is interesting for, say, the COVID situation. What is the probability of, say, testing positive, given that you have the disease? That type of thing. So let's illustrate that, and we'll discuss it. We'll go to the next page here to discuss that. So we will draw a diagram here to illustrate this situation. We will begin by suggesting that we'll say 30% of our population is infected with the COVID virus. That means 30% have the virus, 70% do not. We'll also suggest that when you test, there are only 80% of people who are positive actually test positive. 80% of people who are positive test positive. That means the other 20% actually test negative, even though they're not negative. But we look at another situation, and that is that people who are negative, so actually test positive as well. And we'll just say for now that 10% of people who are negative actually test positive. So that would be a false positive. In other words, you test negative, you test positive, but you actually are negative. Now, these aren't realistic numbers. Perhaps we're just using them to illustrate our probabilities. So, as I mentioned in an earlier module, it's easier to work with fractions, I believe, and proportions than trying to multiply percentages and that sort of thing. So we'll turn this situation into proportions with fractions, and we will draw our tree diagram to illustrate this. So what we're looking at is from our general population, if 30% of people are positive for COVID, and that means that 3/10 of the population are positive. So we'll use red for that. 3/10 of the population are positive for COVID. That, of course, means that 7/10 of the population are negative. So now you go for a test. And using our numbers up here, when you went for the test and you were positive, only 8 of those people actually tested positive. That's 80%. So if 10 people went, it would be 8 out of 10. So the proportion is that 8 out of 10 people actually tested positive who have the disease. And down here we said 10% of these also tested positive, even though they did not have the disease. So that'd be 1/10. That, of course, means that 20%, 2/10 of people with the disease actually tested negative. And in this case, 9/10 of these people did test negative, right? So now we're interested in the following situation. What is the probability that you actually have the disease, COVID? In other words, that you really are positive. And then we put little labels on this. This is a real positive, whereas this is only a T positive, right? Testing positive, as distinct from being really positive. And so again here, testing positive. And then we'll also look at the negative ones. This means you tested negative. This means you really are negative. This means you tested negative. So just look at those again for a moment. So this is really saying you are positive and you tested positive. So that red branch, we'll call it, is those who are positive and tested positive. This mixed branch is those who are positive but tested negative. This branch is those who were negative and tested positive. And this branch is those who were negative and tested negative. So let's just work those out. We'll write them in green. So the probability that you are positive is 3/10. That you tested positive out of that is 8/10. So that means the total probability of that happening is the product of these, 24 over 100. This one is 6 over 100, the probability that you were positive but actually tested negative. That's one you don't want, really. This one is a bit scary, but it's not bad. It's 1/7, it's 7 over 100. So there's a 7 over 100 chance that you're actually a person who doesn't have the disease, but you test as if you have. And finally here, 63 out of 100 is the probability that you don't have the disease and you didn't test for it. I suppose another way of looking at this is kind of imagining 100 people is your total population and 30 of them have it. 24 test positive, 6 didn't. Another 70 don't have it, 7 test positive and 63 don't. But back to up here anyway, we are trying now to see what's the probability that you're positive given that you tested positive. Given that you tested positive. Note that vertical line for given. So we're saying, what's the probability that you really are positive given that you tested positive? Well, the testing positive is actually everything inside this bubble. And I'm going to draw a little bubble here. If you tested positive, you're in this part of the game, right? Oops. I shouldn't have. Not good at drawing these things. Let's see if we get it around again. So the probability of testing positive is made up of the 24 over 100 probability of testing positive when you are positive, and the 7 over 100 possibility of testing positive when you are negative. So therefore, the whole business of testing positive, so you're given that you tested positive, all the possible outcomes so are the 24 over 100, which is one of the possibilities of testing positive. And the other one, the 7 over 100, the probability of testing positive even when you're not positive. But the one that we're really interested in then is the probability of testing positive when you are positive. And in that case, it's 24 over 100. So the thing of interest to us is the 24 over 100. The total possibilities of testing positive are the 24 over 100 and the 7 over 100. So therefore, our probability is the proportion, again, of this nature. And we can see from our learned earlier about fractions, 24 over 100 over 7 over 100 is 31 over 100. And this one is 24 over 100 over 31 over 100. So that will come out to be 24 over 31. So in other words, the probability that you actually have COVID, given that you tested, is just a little over 75%. 24 over 32 would be 3/4, 75%. So this is just slightly larger. But notice how it's not the 80. Now, understanding how that works and looking at the proportions and the tree diagram, I believe, is a nice way of breaking down a problem and looking at it in a very systematic way. And you could play around with this sort of thing. I mean, and look at, suppose there were more false positives. If this number was bigger, then obviously you would notice that if the 7 over 100 is a bigger number, then this overall probability gets lower because this number gets bigger, so the overall fraction becomes smaller. So the more false positives you have, which makes sense, the less chance that you actually have the disease. Likewise, the false negatives, of course, are a more troubling sort of thing, and you could analyze that as well. But I just wanted to give you this basic sort of step-by-step look at a probability example that is very, very relevant to testing for diseases and the false positives and negatives. That will be sufficient on this module. We'll give you a website to explore more of that if you wish.